First and foremost, we would like to greet everybody with a pleasant day. For today is we're going to talk or discuss on divisibility and modular arithmetic. Division. When one integer is divided by a second non-zero integer, the quotient may or may not be an integer. For example, we have 12 divided by 3 is equal to 4 is an integer, whereas 11 divided by 4 is equal to 2.75 is not. Why? Because integer is either a positive or negative whole number, which is 0 is included. Definition. If a and b are integers with a is not equal to 0, we say that a divides b if there is an integer c such that b is equal to ac, or equivalently, if b divided by a is an integer. When a divides b, we say that a is a factor or divisor of b, and that b is a multiple of a. The notation a is divisible by b denotes that a divides b. We write a is not divisible by b when a does not divide b. Theorem 1. Let a, b, and c be integers where a is not equal to 0. Then, if a divides b and a divides c, then a divides the sum of b and c. If a divides b, then a divides bc for all integers c. If a divides b and b divides c, then a divides c. Theorem 2. The division of algorithm. When an integer is divided by a positive integer, there is a quotient and a remainder as the division algorithm shows. Let a be an integer and d a positive integer. Then, there are unique integers q and r with 0 less than or equal to r less than d such that a is equal to ds plus r. Examples. Determine whether 3 divides 7 and whether 3 divides 12. We see that 3 is not divisible by 7 because 7 divided by 3 is not an integer. On the other hand, 3 divides 12 because 12 divided by 3 is equal to 4. The second example is, what are the quotient and remainder when 101 is divided by 11? Solution, we have 101 is equal to 11 multiplied by 9 is equal to 99 plus 2 is equal to 101. Hence, the quotient when 101 is divided by 11 is 9 is equal to 101 divisor of 11, and the remainder is 2 is equal to 101 modulo of 11. Modular arithmetic. In some situations, we care only about the remainder of an integer when it is divided by some specified positive integer. For instance, when we ask what time it will be on a 24-hour clock 50 hours from now, we care only about the remainder when 50 plus the current hour is divided by 24. Because we are often interested only in remainders, we have special notations for them. We have already introduced the notation a modulo of m to represent the remainder when an integer a is divided by the positive integer m. We now introduce a different, but it's related, notation that indicates that two integers have the same remainder when they are divided by the positive integer m. If a and b are integers and m is a positive integer, then a is a congruent to b modulo of m if m divides a less b. We use the notation a congruent to b modulo of m to indicate that a is congruent to b modulo of m. We say that a congruent to b modulo of m is a congruence and that m is its modulus. If a and b are not congruent modulo of m, we write a is congruent to b modulo of m. Theorem. Let a and b be integers and let m be a positive integer, then a congruent to b modulo of m if and only if a modulo of m is equal to b modulo of m. Recall that a modulo of m and b modulo of m are the remainders when a and b are divided by m respectively. Consequently, Theorem 3 also says that a congruent to b modulo of m if and only if a and b have the same remainder when divided by m. Theorem: let m be a positive integer if a congruent to b modulo of m and c is congruent to d modulo of m. Then a plus c congruent to b plus d modulo of m and ac is congruent to b d modulo of m. We use a direct proof because a is congruent to b modulo of m and c congruent to d modulo of m. By the theorem, there are integers s and t with p is equal to a plus sm and d is equal to c plus tm. Hence, b plus d is equal to a plus sm plus c plus tm is equal to a plus c plus m multiplied by the sum of s and t, and bd is equal to a plus sm multiplied by c plus tm is equal to ac plus m multiplied by the sum of at, cs, and stm. Hence, a plus c is congruent to b plus d modulo of m, and ac is congruent to bd modulo of m. Examples: determine whether 17 is congruent to 5 modulo of 6 and whether 24 and 14 are congruent modulo of 6. Because 6 divides 17 less 5 is equal to 12, we see that 17 is congruent to 5 modulo of 6. However, because 24 less 14 is equal to 10 is not divisible by 6, we see that 24 is not congruent to 14 modulo of 6. Because 7 is congruent to 2 modulo of 5 and 11 is congruent to 1 modulo of 5, it follows from the theorem 5 that 18 is equal to 7 plus 11 is congruent to 2 plus 1 is equal to 3 modulo of 5, and that 77 is equal to 7 multiplied by 11 is congruent to 2 multiplied by 1 is equal to 2 modulo of 5. We have also the applications, which is the cryptography using modular arithmetic. One of the earliest known uses of cryptography was by Julius Caesar. He made messages secret by shifting each letter 3 letters forward in the alphabet, sending the last 3 letters of the alphabet to the first 3. For instance, using this scheme, the letter B is sent to E and the letter X is sent to A. This is an example of encryption, that is the process of making a message secret. For encryption, P is equal to P plus 3 modulo of 26. What is the secret message produced from the message "Meet you in the park" using the Caesar cipher? First is replace the letters in the message with numbers. This produces 12, 4, 4, 19, 24, 14, 20, 8, 13, 19, 7, 4, 15, 0, 17, and 10. Now, replace each of these numbers P by Fp is equal to P plus 3 modulo of 26. This gives you 15, 7, 7, 22, 1, 17, 23, 11, 16, 22, 10, 7, 18, 3, 20, and 13. Translating this back to letters produces the encrypted message PHHW BRX LQ WKH For decryption, Fp is equal to P less 3 modulo of 26. Decrypt the message PHHW BRX LQ WKH using Caesar cipher. Solution: first, is replace the letters in the message with numbers. This produces 15, 7, 7, 22, 1, 17, 23, 11, 16, 22, 10, 7, 18, 3, 20, and 13. Now, replace each of these numbers p by fp is equal to f less 3 modulo of 26. This gives you 12, 4, 4, 19, 24, 14, 20, 8, 13, 19, 7, 4, 15, 0, 17, and 10. Translating this back to letters produces the encrypted message, meet you in the bar.